1. Introduction to chemistry. Why does a study of all these ideas deserve your attention? There are good career reasons for one thing. Chemical firms and many non-chemical firms require knowledge of chemistry, and people with this knowledge are proportionately rewarded. There are many other reasons though. Nations that have raw materials but must import many of the things made from these materials cannot advance in prosperity as rapidly as those who can make these things. With a good knowledge of chemistry, you would be able to work toward a stronger community and a stronger country in these ways. Finally, a knowledge of something removed somewhat from the hurly-burly of ordinary living will lend a stability and balance to your thoughts and actions that will be hard to achieve otherwise. We begin our study of chemistry with a fairly detailed account of the physical and chemical properties and uses of the 112 known elements. We shall follow that account with a quite comprehensive study of compounds formed by various combinations of these elements. A brief mention will be made of many of the simpler organic compounds. A reaction is observed whenever two or more substances interact and form one or more new substances. This subject is one of paramount economic importance, since the products of chemical reactions form, support, and surround us. All production industries and many service industries are predicated on the need for the reactions that are discussed. Definition and scope of chemistry. At their simplest, the basic units of chemical sensing, collection of quantitative chemical data, and feedback electronic interactors are small compounds. Small molecule pharmaceutical compounds, highway construction materials and fuels are examples of materials. Many of these are noble offshoots of advanced chemical processes. Who can imagine life without medical drugs, plastics, or computer hardware? Countless samples of food, cosmetics, fuels, and artificial textile fibers are the results of important chemical transformations. In fact, there is virtually no aspect of life in the world that can function without intervention and influence from chemical processes. It is important that the people who carry out and carry on work in chemistry be given a viable, sophisticated, and understandable introduction, a flexible and operative roadmap, for their initial steps into the submicroscopic world and the ideas of chemistry. Chemistry encompasses a broad range of subject matter that is studied at all levels of the educational ladder. From the most rigorous theoretical mathematical computations to the simplest possible experimental processes and sample preparations, the knowledge or investigations derived from the knowledge in the study of chemistry is designed to contribute to a better and more rational understanding of the world. Chemistry also aspires to contribute to the development and improvement of materials, drugs, foods, flavors, and fragrances, and to provide a range of technological services and viable economic activities. The most important branch of chemistry today is undoubtedly connected with the development of materials, often within the great mechanical and space engineering interests. Importance of chemistry in everyday life. The impact of chemistry on society can be seen and felt in our daily lives, right from the miraculous cures for various diseases we benefit from, the food and nourishment we consume, the clothes on our backs, the personal care applications we use daily, to the basic materials found in many of the things we use daily. Chemists make materials and create, transfer and store energy, all in the quest of making our world a better place to live. In a nutshell, almost every aspect of life involves chemistry. Without chemistry, a hard day's work would not leave a person so exhausted. Chemistry is a branch of science that attempts to study the components of substances that make up our world. Further, chemistry tries to understand the interactions that take place between different types of matter. In order to understand and appreciate the importance of studying chemistry, one has to consider the importance of chemistry in the various areas that chemistry comes into contact with. Consequently, one will appreciate how chemistry plays a vital role in our daily lives. The structure of an atom. Inside the electron cloud, there are energy levels. This is where the electrons are found spinning around the nucleus. Each energy level has a specific capacity. The first energy level is the closest to the nucleus and has the lowest energy capacity, while the closest to outer levels have a larger energy capacity. The first energy level can only hold 2 electrons, the second energy level can hold 8, the third energy level can hold 18, and the outer level would be able to hold 32 electrons. The fourth, of course, would hold the most, because electrons get to the outer shell and get pulled to other atoms. These energy levels can also have sublevels, which contain orbitals. Orbitals are the different shapes that electrons can travel in, as the atom moves throughout its energy levels. The first sublevel is known as the s orbit, the second sublevel is known as the p orbitals, the third sublevel is known as the d orbit, and the fourth sublevel is known as the f orbitals. The atom is made of 3 parts: protons, neutrons, and electrons. Protons and neutrons are found in the middle of the atom, while electrons spin around the outside. The protons, or positively charged particles, are much larger and weigh a lot more than an electron. Protons and electrons have equal but opposite charges, which is what holds them together inside the atom. The electron cloud is negative, and the positive nucleus is in the center of this cloud. The opposite charges of the electrons and the nucleus are what hold the atom all together. Neutrons are also found in the center of the atom. Subatomic particles: protons, neutrons, electrons. When you weigh the first 92 uranium's atomic number elements on a scale, most of the weight is from the protons and neutrons, 75 to 99% of the total mass in almost all cases. The electron mass adds so little that it is usually disregarded. Protons are positively charged, neutrons are neutral, electrons are negative. Protons contain 3 up quarks and neutrons have 2 down quarks and 1 up. Because they are oppositely charged, protons and electrons attract. In their natural state, atoms have an equal number of electrons, making them electrically neutral. Protons have a mass of about 1 atomic mass unit, AMU, and electrons' positions are 1800 times lighter. Protons and neutrons are massive particles, having a nearly 2000 times greater mass than an electron. Historically, many scientists asked why the atoms of visible matter do not have matching numbers of electrons and protons, causing large-scale particle attractions or repulsions. Atoms remain neutral because of equal positives and negatives. For more than 2000 years, ideas about what makes up matter have, at various times, included 4 elements: earth, water, air, and fire, or as many as a dozen more. Today, because of chemical tools and theories, scientists have many ways to envision atoms, and all of them involve much tinier building blocks than fire, earth, water, and air. A neutral atom has the same number of electrons orbiting as it does protons in the nucleus. The number of protons is what identifies the atom. It is called the atomic number and determines the properties of the element it distinguishes. Protons are in the atomic nucleus of every atom. In certain elements, the nucleus also holds some number of neutrons. An electron circles the nucleus at some distance and energy level, held there by the attraction of opposite charges within the atom. Atomic number and mass number. Each element can exist as several nuclides, which are atoms that contain the same number of protons but different numbers of neutrons. For example, carbon, with the chemical symbol C and the atomic number 6, exists with an atomic mass of 12, 13, and 14. The isotopes with mass numbers of 12, 13, and 14 are known as carbon-12, carbon-13, and carbon-14, respectively. The mass number can also be written as a superscript to the left of the element's abbreviation. However, all isotopes of carbon have 6 protons in their nuclei and therefore belong to the same element. As we will see, different isotopes of an element have different chemical properties, but for the purposes of studying chemistry, the individual isotopes of an element are effectively identical. An element is defined by the number of protons contained in the atomic nucleus, and all atoms of an element have this same number of protons. Some elements can exist in several functional forms, which are called nuclides. The different nuclides of an element contain the same number of protons, but have different numbers of neutrons in their nuclei. Thus, nuclides of an element have the same atomic number but different mass numbers. Nuclides are indicated by the notation Z, where A is the chemical symbol of the element and A is the mass number. For example, the common isotope of carbon is denoted C with a mass number of 12. It is carbon with Z equals 6 protons and 6 neutrons. The number of protons in the nucleus is also known as the atomic number, and it is usually written as a subscript to the left of the element's abbreviation. The mass number is the sum of the number of protons and neutrons in the nucleus of an isotope. The periodic table. The table contains so much information that scientists can use this information to predict as yet undiscovered elements and their properties, and look for them in the lab. The smallest part of the table is called a cell, and each element has a cell to describe it. The cells that list the same information have been grouped together. Some groups have a title, such as the alkali metals. These all contain a single electron in their outer shell, and this means they have similar chemical properties. Each cell contains a lot of information about the element, much of which we have described previously. For example, we have already described how to determine the number of protons in the nucleus of an atom, or how to predict its mass, and most everything else is derived from rules that chemists have developed from observation. The periodic table is perhaps the single most important concept in chemistry. The table has a lot more information, but one easy way to remember the information is with a one-sentence summary, such as, the lanthanides are a series of elements from period 6 that are all metals. This is a massive oversimplification, but it helps to set the landscape. The periodic table is a table of the elements, but it is more than that. It is a table of what is known about the elements. The table has room for all of the remaining known elements, but they have not been discovered yet. In fact, chemists are actively searching for new elements, but the decay rate of many of these elements is measured in seconds. Organization of elements. The periodic table has more rows or periods than the one found in the science classroom because of how we now understand atomic structure. The highest energy levels in the row are partially filled with electrons. The periodic table has 7 rows, which are called periods. Elements that are in the same column, or group, up and down, of the periodic table go together and have the same number of electrons in the outer energy level. The number of protons, electrons, and neutrons in all matter are related to each other, and they never change in ordinary chemical or physical changes. The periodic table has 18 columns, which are called groups. The modern periodic table is the new way to organize the chemical elements, which are the basic building materials or make up all matter. Elements are substances that cannot be broken down into a simpler substance, and they are made of only one kind of atom. The modern periodic table takes the work from earlier scientists and uses recent information from physics and chemistry. The horizontal rows or periods on the periodic table tell the number of energy levels an element has. The modern periodic table is organized in a way that groups elements with similar chemical and physical properties together. Periods and groups. The alkali metals make up group 1 of the periodic table, from lithium to francium. All alkali metals have a single electron in their highest energy level, N equals 1, and are highly reactive. Their reactivity increases moving from the top to the bottom of the group. The alkali metals are soft metals that are silver-white in color. The alkaline earth metals make up group 2 of the periodic table, from beryllium through radium. Like the alkali metals, the alkaline earth metals are not found uncombined in nature. The alkaline earth metals have 2 electrons in their highest energy level, N equals 2, and are highly reactive. The reactivity increases moving from the top to the bottom of the group. Unlike the alkali metals, the alkaline earth metals are not as soft and have somewhat higher melting points. The halogen elements make up group 17 of the periodic table, from fluorine to astatine. All of the halogens have 7 electrons in their highest energy levels. These elements form salts when they combine with hydrogen and are diatomic in nature. The elements in the periodic table are arranged in periods rows and groups columns. The arrangement emphasizes the way in which the electron structures of elements respond to the filling of the appropriate energy levels and sublevels. Both the period and the group of an element can be used to predict key characteristics of the element. In this section, we investigate elements from the alkali metals, the alkaline earth metals, the halogens, and the noble gases in their respective groups. Chemical bonds. In order to end up with full valence shells, the cations will give their valence electrons to the anions, which then become negatively charged when they take on more electrons than they have protons. The positive charges from the cations become attracted to the negative charges on the anions, and the result is an ionic bond, which is a type of chemical bond that forms from the attraction between oppositely charged ions. These attractive forces hold the ions together into a stable compound, known to be an ionic compound. Due to their strong attraction between ions, ionic compounds tend to have a very high melting and boiling point, since a large amount of energy is needed to overcome the attractive forces. Unless in solution, ionic compounds will conduct electricity when dissolved in H2O, because the ions become mobile and can carry an electrical current. As mentioned in the previous section, atoms will for the most part undergo chemical reactions if it allows them to end up with 8 valence electrons, if they're in the s or p orbitals, or in the special case of helium, 2. This is known as the octet rule, or the duet rule for helium. In order to obtain the 8 electrons needed for a full outer shell, or the 2 most of the elements actually need, other atoms will lose or gain or share their valence electrons. This portion of the periodic table is where the non-metal and metal elements are located. The p or s elements, which are more likely to gain electrons to become negatively charged anions, are on the right side of the periodic table, while the s elements, which are more prone to lose electrons to become positively charged cations, are on the left side. The octet rule does not apply to transition metals, which will give up varying amounts of electrons to become cations with varying charges. Ionic bonds. The name of the cation is usually the same as the name of the element that formed it, and the name of the anion is the root name of the element plus -ide. When naming ionic compounds, the cation is always named first. The complete formula of the compound is neutral, so the charges on the cations and anions in an ionic compound must be balanced. The number of positive charges on the cations should be equal to the number of negative charges on the anions. In this way, the electrostatic attraction keeps the ions bonded. The result is that ionic compounds are neutral overall. When pure elements combine to form ionic compounds, the valence electrons necessary to complete the octets of the atoms most often are transferred between the atoms. The interaction between oppositely charged ions in an ionic compound is called an ionic bond. The label ionic is used to designate the bonding that occurs when the electrostatic force of attraction between ions of opposite charge holds the particles together. Ionic bonds form between a metal from the left-hand side of the periodic table and a non-metal from the right-hand side of the periodic table. The element that forms the cation is always on the left and top of the periodic table. Another way of predicting those common cations is through the periodic table group numbers. Covalent bonds. The attraction between the atoms of a covalent bond is known as a covalent bond. The bond length is the distance between the nuclei of the bonding atoms. The distance between the nuclei of 2 atoms bonded together is the bond length. Characteristics of covalent bonds. 1. The bond length of a covalent bond is measured in angstrom units, A. 1A equals 1 by 10⁻10 meters. 2. The strength of a covalent bond is defined by the amount of energy necessary to break the bond. The energy required to break a covalent bond is known as bond energy. Among the covalent bonds, the triple bond is the strongest, the double bond is the second strongest, and the single bond is the weakest. Bond energy, kilojoule per mole, is the energy necessary to break a covalent bond. 3. Covalent bonds are equal or shared electrons. Equal sharing of electrons between atoms with the same atomic number, consisting of one or different elements, is called the non-polar covalent bond. On the other hand, the shared electrons between atoms with different electronegativities form a polar covalent bond. How many valence electrons do atoms like oxygen, nitrogen, and carbon have in their outermost energy level? The answer is 6, 5, and 4. Atoms need 8 to become stable. What might they do then? Give away their 6, 5 and 4 electrons and become positively charged, or share some electrons with other atoms in order to achieve the same goal but without becoming charged. Which one do you think is going to be the likely choice for them? These atoms are not giving up their valence electrons, but they prefer to share them to achieve noble gas-like configurations. When electrons are shared between atoms, a covalent bond is formed. A covalent bond is a chemical bond formed by the sharing of a pair of electrons. A single covalent bond is formed when only one pair of electrons is shared between atoms. A double covalent bond forms when 2 electron pairs are shared, while a triple covalent bond forms when 3 electron pairs are shared by 2 atoms. Chemical reactions. All of this talk about chemical combinations and changes will bring us to the topic of chemical reactions. Reacting is when substances change to form new substances. These new substances only form when the original substances change chemically. The only real evidence that a chemical reaction has occurred is the appearance of new substances. The new substance is the result that tells us that a reaction has occurred. Some other evidence of a change of reaction might concern changes in physical properties, like odor, color, or state of matter. Matter can also give off heat or absorb heat during a reaction. The reaction can also produce light, electricity, or sound. Often, the key to producing a reaction is heat. All of this evidence is the result of another rule of matter. This rule is, matter cannot be created or destroyed in a chemical reaction. It may seem like matter is being created or destroyed, but it is really only being changed. The answer to this story is that changes in matter are all the result of atoms. These atoms look for a balance of either losing, gaining, or sharing electrons. With the release of energy produced by their arrangement, the balancing act between the electrons causes the particular properties that the substance can display. Types of reactions: synthesis, decomposition, single replacement, double replacement. It can be read as 2A and AB become AB. Heat is often needed to make the reaction happen. This is an example of the general equation for a synthesis reaction. 2A plus B, right pointing arrow AB. The simplest synthesis reaction combines 2 single elements and forms a compound. The elements may be metals, metalloids, or non-metals. This is the general form of the synthesis reaction. There are 4 different types of reactions that we are going to study in this unit. A reaction is the process in which parts are being reunited and a chemical change happens. The breaking and forming of the bonds is what ensures that there is a new substance at the end of a reaction, even though it may not look like a new substance. This is where chemical properties are important. As chemical properties change, a new substance is formed. The 4 reactions that we are going to study are as follows: synthesis, decomposition, single replacement, and double replacement reactions. Balancing chemical equations. Balancing an equation is the process of adjusting the subscripts and coefficients until each side of the equation has the same number of atoms of each element. The subscripts can never be changed when balancing equations, as changing subscripts would change the formula of the substance and therefore change the identity of the substance. The coefficients before the reactant or product names can be the same, as they are only implied multiplication. Be aware, however, that when balancing equations with polyatomic ions as reactants or products, the polyatomic ion must stay together as a group entity. Balancing chemical equations does not mean doubling the number of atoms of one element on one side of the equation and cutting the atoms of the other element in half. On the other hand, one must be careful not to disturb the chemical formula of a product or a reactant while balancing the equation, as the substance may change its identity. The law of conservation of mass mandates that the quantity of each element before and after a chemical reaction must be the same. In describing a chemical reaction, one should place an equal sign between the names of the reactants and the names of the products. However, since the matter before and after a reaction must be the same, the numbers of moles on either side of the equation must be equal. It is often necessary to modify the coefficients before the reactant and product names to fulfill this requirement. This process is known as balancing the equation. States of matter. When a force is exerted on a solid, the solid changes its shape. As a result, a solid deforms. Stress, the measure of the force acting on a material, is the force divided by the area. The SI unit of force is the Newton, and while the preferred SI units of the other quantities involved in the formula are pascals and square meters, a common non-SI unit of stress is the pascals equal quantity, the N per square meter. A key characteristic of both gases and liquids is their ability to flow. Consequently, both gases and liquids are called fluids. Gases and liquids have similar behaviors because their particles are not locked into fixed positions. Instead, the particles slide past one another. As a result, neither a liquid nor a gas has a shape of its own. In the absence of any external force, a liquid assumes the shape of the wall of its container. A gas spreads uniformly to fill its container. Therefore, the shape of a gas is not confined to the position of the wall of its communicating vessel, and this gaseous behavior makes it widely and readily distributable in the atmosphere. Stress is the measure of the force applied to a material, and is the force divided by the area over which it is applied. The SI unit of stress is the pascal, which is defined as 1 N per square meter. However, when force is applied to a fluid, either a gas or a liquid, the normal perpendicular force exerted by the fluid does not remain constant. Instead, it depends not only on the pressure exerted by the fluid, but also on the shape of the material. The value of stress is computed using the formula stress equals pressure times strain, in which the strain is the ratio of the change in the dimensions of the material to the original dimensions. Matter can exist in 3 different states, depending on the arrangement and behavior of the particles involved. When a force acts upon a liquid, the liquid does not undergo a change in shape. In contrast, a gas undergoes both a change in shape and a change in volume. As a result, a gas is much more compressible and expandable than is a liquid. Solids are characterized by their ability to diffuse stress without suffering any deformation. When stress is applied to a solid, the solid does not flow. It retains its shape and volume. Solid, liquid, gas. In stepping through the first reaction, we saw that the new product was made from 2 solids, baking soda and acetic acid. This solid product reacted with baking soda and acetic acid to form a solid, sucrose. Conversely, this time, a liquid, water, was produced instead of a solid sugar product. Chemists are very much interested in the state of matter that is produced, of course. However, when they want to take an exam, such as to evaluate the progress of the reaction, they want to evaluate the reaction in a vessel that is easy to observe. For this purpose, they can evaluate the reactants or the product as solids. Liquid. It is very difficult to observe the reaction when it is occurring because we can see right through liquid phase-like vessels, and because reactions that occur in the solution phase, such as some chemical and biological processes, last for a short while, making the completion of the reaction difficult to determine. When you perform the reaction between baking soda and acetic acid, you watch the solids change. In every chemical reaction, things can change into solids, liquids, or gases. So chemists always learn to reorganize the materials involved in the reaction, so that they can carry out their work however they wish. Most commonly, chemists will transform a given solid chemical into liquid or solution form, so that the completion of a reaction can be determined, or so that the product can be isolated from the reaction mixture. Once the reaction is done, chemists commonly want to change the new product, which is in a solid state, to liquid or solution form so that the product can be isolated. To do this, another type of separation technique, such as recrystallization or evaporating solvent, is employed. Section 6.5. The following examples illustrate these 2 types of reorganization of physical states. Phase changes. When heat is added to a solid, the input of the heat energy is used to increase the temperature of the solid. The amount of heat energy absorbed depends on the phase of the solid. When the temperature of the solid reaches a critical point, additional heat energy results in the phase change of the solid to a liquid. The heat energy input is then used to increase the temperature of the liquid to another critical point, at which time the liquid solidifies. At this point, heat is released as the solid forms. This sequence can be visualized in the heating curve. The flat portions of this curve represent areas where heat energy is being used to change the phase of a substance, rather than change its temperature. It takes a certain amount of heat energy to change the phase of a substance at a certain temperature. This amount of heat energy is called the heat of fusion. The heat of fusion is the number of joules of heat energy needed to change 1 gram of a substance at a certain temperature from a solid to a liquid. Acids and bases. An acid and a base, when brought together in a water solution, usually react to form a neutral material called water and a compound called a salt. Salt is defined as a substance that contains a metal and a non-metal. You have observed that most acids and bases taste different. Unfortunately, tasting them to determine if a solution is acidic or basic is not a very safe way to do it. Another way that you can determine if a substance is an acid or base is by testing it with litmus paper. Like tasting acids and bases, there are disadvantages to using litmus paper to test for the presence of an acid or base. In the 18th century, 2 scientists, Lavoisier and Davy, discovered that acids are substances that contain the element hydrogen. They learned that when an acid dissolves in water, it breaks apart, releasing the hydrogen ions. They also found that a large enough concentration of hydrogen ions will cause significant changes in certain substances. A base is an alternative name for a compound known as a hydroxide, that is, compounds that break apart in water and release the negatively charged hydroxide ions. Lavoisier understood that most bases contain oxygen and hydrogen. When a significant number of hydroxide ions are released, the solution is classified as a base. Properties of acids and bases. In the reaction shown previously, the type of acid secreted by the taste cells is determined by the type of acid secreted by the previous type of acid. For example, when a human cell releases hydrogen ions into water to make it acidic, lactate, a base, is released to return it to its natural state. In contrast to acids, acids release hydrogen ions into water to make them acidic. However, the hydrogen ions formed by the reaction are quickly removed through reaction with lactate. In contrast to acids, bases release hydroxide ions into water to make them basic. When a base reacts with another compound by giving the hydroxide ion, it is a basic reaction. It does not have to include water. In addition to tasting sour, properties of acids include conducting electricity, turning blue litmus and red cabbage juice red, and reacting strongly with bases and less vigorously with metals. Properties of bases include tasting bitter, conducting electricity, feeling slippery, turning red litmus light blue, and reacting vigorously with acids and less strongly with metals. pH scale. pH: acetic acid, hydrochloric acid, 0100 1902 803 4567 1891 001112 1314 15 1617. This relationship is also so important that it is used to define a second type of logarithmic scale, the pK, which is used to measure the ionization of weak acids. A plot of pH versus the percent ionization for hydrochloric acid and acetic acid is shown below. pH plus Po equals 14. The sum of the pH and the Po equals 14. Po equals log OH. The Po is defined as the common logarithm of the reciprocal of the hydroxide ion concentration and is given by pH equals log H plus. This relationship is so important that it is used to define the pH scale. The pH is defined as the common logarithm of the reciprocal of the hydrogen ion concentration and is given by Kw equals H plus OH. Recall that in pure water, we defined the ion product of water. Organic chemistry. We've emphasized carbon because there's a huge number of organic compounds out there. They are derived from the element carbon, and all living things are composed. Matter is composed of carbon compounds. A lone carbon atom will generally bond to both carbon and hydrogen, and along with other atoms, these atoms act as a kind of nucleus, which is found in an element because of similar atomic properties. With the possibility of so many different combinations of carbon structures, and the clever method carbon uses to bond with other atoms, it's no wonder there are so many organic compounds. No agriculture here. Inorganic chemicals are called inorganic because they are found in minerals, i.e. salts, rocks, materials that are not organic. And all rocks, stone or pebbles are quite unsafe for human consumption. Hence, organic has less to do with agriculture and more to do with human life. If it's alive, if it's in plastic, rubber, sugar, starch or gasoline, it's organic. At its most basic level, organic chemistry is the study of carbon compounds. And for anyone who's ever heard an alarmist newscaster warn about lethal toxic chemicals, this might come as a good piece of news. Organic compounds equals safe to eat. They're called organic because they are produced in nature. That's why a soft drink is called a carbonated beverage, and leather, cloth and cotton can also be called organic crops. You have probably heard the phrase organic chemistry sometime in your life, but if it has this moment conjured up some mysterious combination of science and agriculture, you are forgiven. After all, the word organic is used to describe foods grown without the help of chemicals, and the word inorganic is used to describe everything else. If that's all you know and assume that organic chemistry is merely the study of vitamins and such, it's definitely time to make amends in your head. Organic chemistry has to do with a lot more than cooking vegetables and fruit. Hydrocarbons. Hydrocarbon is a term used for compounds that contain only the elements of carbon, C, and hydrogen, H. A hydrocarbon can be an acyclic, branched, or cyclic molecule, and may be saturated or unsaturated. The simplest organic compounds are saturated hydrocarbons, and they are composed of single covalent bonds between carbon atoms in a chain. The straight-chained unbranched or non-branched hydrocarbons are sometimes called N-alkanes. Alkanes have very little reactivity because they are saturated compounds. Their reactions include combustion, halogenation, free radical halogenation, and pyrolysis. Alkanes are a family of compounds whose molecular formulas are CnH2n+2. All alkanes are composed of just hydrogen atoms, and carbon atoms are chemically bonded structural shapes that are commonly called tetrahedrons. When a hydrogen atom is replaced by another atom or functional group, a new family of compounds or molecules is formed in place of that family, in which that original atom or functional group justified a new family name, which is based on the name of the original no more in the family. Through this concept, functional group names are developed and used to identify families in organic molecules. Hexane is often used as an organic solvent and is used in the industrial production of gasoline. There are many different types of organic compounds, but they all have one thing in common: they contain the element carbon. For this reason, the field of organic chemistry, concerned with compounds containing carbon, is a branch of chemistry that deals with compounds of living organisms and the material derived from them. Carbon forms many compounds with the other main group elements. For example, hydrocarbons containing only carbon and hydrogen compose an entire branch of organic chemistry. Many organic compounds are built up from hydrocarbons, so understanding of hydrocarbons is both fundamental and useful for further study of organic chemistry. Functional groups. At first, it may seem cumbersome to define organic molecules composed of predominantly multiples of only two structural components. Why not be content with simply identifying reaction sites, and then dealing with the various general types of chemical reactions that can occur? The answer is that most of the principles of structure and reactivity that can be established for simple hydrocarbons can be generalized to encompass a much broader array of organic molecules. By simply concentrating on the reaction sites within a small subset of hydrocarbons, we are able to draw far-reaching conclusions about reactivity. The most commonly encountered functional groups can then be identified by comprehension of the properties of these types of compounds. The relatively small number of general overarching principles for organic compounds make chemistry an especially cohesive science. By focusing on atoms participating in reactions, we have already introduced the classification of molecules, particularly organic molecules. The diversity of molecules can be organized by classifying them according to the components of which they are composed. Organic molecules can be composed of hydrocarbon portions and functional groups. Hydrocarbon portions, such as CH2 or aromatic ring systems, serve as the skeleton of an immense number of organic compounds, while functional groups are the parts of the structure that are largely responsible for the physical and chemical properties of a compound. Environmental chemistry. As has been pointed out many times, people go into professions that they know something about. The more chemistry is involved in the course taken by a functioning adult, be it auto mechanics, teaching, retail selling or the like, the more likely it is that this person will have a deeper appreciation of the scope of chemistry as it affects us all and the environment in which we live. In recent years, environmental chemistry has been receiving increased attention. Perhaps this is because of the growing and overlapping concerns over drinking water quality, land-based and underground storage tanks, air pollution, and other issues generally deemed to be environmental. It seems fitting, therefore, that we end this book with a brief discussion of some of the many ways in which chemistry affects us, and how we are affecting the environment. A great many experiments in environmental chemistry can be performed by individual citizens on a participatory basis. Pollution and remediation. Pollution can contaminate the drinking supply, both in water dams and reservoirs, and in our underground water supply. The list of substances found in water includes lead, nitrates, and chlorides. Pesticides and PCBs originating from fields can destroy fish life in lakes and streams. The presence of metals in river water originating from mine waste is known in Canada by the term acid rain. In Ohio, as with many other regions of the United States, underground water is being depleted at a rate greater than the rate of replenishment. Consequently, salt water from the ocean is seeping into the groundwater supply. The increased levels of mercury in Ohio's fish have caused state regulations on the number of fish deemed acceptable to be eaten. Unfortunately, the high levels of mercury in the fish cannot be changed. The excessive amounts of mercury found in the fish are a result of deposition from industries that burn fossil fuels. Agencies are closely monitoring sewage sludge directed to farmland. The presence of such heavy metals as lead, cadmium, and mercury have been tested. It would be unthinkable that we have to continue talking about an absence of laws to govern the release and presence of harmful elements in the environment. Furthermore, due to pollution, over 40% of our lakes are not clean enough to support fish life. Upon hearing these statistics, society becomes aware of what really constitutes pollution. The term pollution means many things to different people. An innocent child playing with a puppy and being hit over the head by a drunk staggering from a bar evokes immediate images of air and water pollution. A city bus rolling over this same innocent child creates a feeling of pollution in our society. Environmental pollution refers to substances that are released into the air, water, soil, as well as to harmful bacteria, food supply, pesticides, detergents, plastics, and clothes that can result in air and water pollution. Pollution can come from ways too numerous to list, while the adverse effects of pollution are too serious to disregard. In the United States, the National Academy of Sciences has reported that air pollution has been linked to lung disease, heart trouble, emphysema, cancer, birth defects, altered heredity, and even death. Climate change and green chemistry. According to the planet's leading scientific institutions, growing evidence shows that human activities are altering Earth's climate. Over the course of Earth's geological history, greenhouse gases have been responsible for driving the climate, changing the climate from hot to cold and back to hot. This time, however, it is the rapid increase in greenhouse gases generated mostly by human activities that is causing concern. The observed increase in global temperature during the past half-century is due primarily to human-induced emissions of heat-trapping gases. The consensus view of the scientific community is well represented by the Intergovernmental Panel on Climate Change, IPCC, which has been established to assess this scientific information for the United Nations. The IPCC brings together the world's leading climate scientists and hundreds of expert reviewers to provide periodic assessments of the current state of knowledge on several important climate issues. Its most recent 2007 report concluded that the warming of the climate system is unequivocal, and that most of the observed increases in global average temperature since the mid-20th century are very likely due to the observed increase in anthropogenic, human-induced greenhouse gas concentrations.